So a little bit more. Not much. Right. So we've done a star connected system. Yeah. Relationship between phase and line currents for a delta connected system. So in delta, we've got a line voltage. Okay. Can you see that the voltage across each phase of the load, the voltage across that load must be EL. The voltage across that load is the line voltage between this phase and this phase, there. And the voltage across this load is the difference between those two phases, there. So in delta, line voltage and phase voltage are equal to each other. So that's the opposite, really, of a star, where the currents were equal in star. Line current, phase current were equal. In delta, line voltage and phase voltage are equal. Again, something you've got to remember or sketch a little diagram to remind yourself that phase, you must have this voltage, EL. Yep. But if we look at the currents, sorry? Yeah. Alright?
Yeah, don't worry about it.
Don't worry about it. It's too late in the day for thinking. Right. We've got a current flowing in each phase. I1, I2 and I3. Alright? If we focus on this top section, right? Again, like the Kirchhoff's voltage law, right, I have this rule of everything that goes into that junction has to leave it in some direction. Alright? And therefore, we can write all the currents going in one side and all the currents leaving that junction on the other side. So if we do that up here, IA is going in, yeah, I3 is going in, and I1 is leaving. Alright? Depends which way round you put the arrows on, of course. Okay? But can you see that the line currents and the phase currents have to be different? If I rearrange that, do I get what I got over the other side there? IA is equal to I1 minus I3. Yeah? So this line, what's it saying is, this line current, a little of it's going down there, and some of it's going down the phase. I've got two ways to go. Yeah? Which way the arrow should be at any instant in time depends on where it is in the cycle around the generator that's generating the electricity that produces it. We must remember, when you're talking about AC, as you can always be instant in time, current is in this direction. Milliseconds later, that arrow could technically be the other direction. Alright, so you just fix and say, that one's that way, that one's that way, and you could end up with a negative current because of it, but that just means you put the arrow on the wrong way. Okay, so you mustn't get too hung up about that. Alright, so again, what we can do is draw phasor diagrams involving the currents this time. Come back to our old friend. There's the line current set at 0. Okay. We know it's 30 degrees out of phase with our line voltage from the previous Talking of it, okay. We've got our other two currents. So we produce this triangle again with our 120 degrees, our 30 degrees, and the length of that line, and the length of that line. We end up with IL over sine 120 is equal to I1 over sine 30. Rearrange that, we end up with the line current is root 3 times the phase current. So, the line current in a delta system is bigger than the current in each phase. Yep. And you can get it from the diagram because of the fact that some of that current goes one way, some goes another way. They contribute to the overall currents travelling at any one time in the legs of that delta system. So in summary, for a star-connected system, IL is equal to root 3 times I1. And that never changes. Current voltage, yeah. Yeah. So, the easiest way I think to remember is, particularly if you're an electrician and you know voltage across two phases 400, and that's the line voltage. Voltage between phase and neutral is 230 volts. You know that in a star-connected system, line voltage is root 3 times the phase voltage. Yeah, and then remember that delta is opposite. That's the current. That's root 3 times phase current. All right. If you're given the line current, then you can divide by root 3 to get the phase current. So you can rearrange that little formula, that one there, can't you? If you're given the line, if you're given the phase current, you can divide. If you're given the line current, you can divide the line current by root 3 to get the phase current, and so on. All right. Last thing I'm going to do tonight is sum up on the two different systems, and we'll pick up on the calcs regarding the three-phase systems next week. All right. So, just in summary, in a star-connected system, the line voltage is root 3 times the phase voltage, and the line current is equal to phase current. The three line voltages are 120 degrees out of phase with each other. The three phase voltages are 120 degrees out with each other and 30 degrees out of phase with the respective line voltages. You can see that here. There's two of the line voltages. One voltage phase, that phase voltage. And then in a delta connected system, line current is root 3 times the phase current. Line voltage is equal to phase voltage, and three phase currents 120 degrees at phase with each other. Three line currents 120 degrees out of phase with each other, and 30 degrees out of phase with their respective phase voltages. So if I was to put the other currents on this diagram, there'd be one down there, there'd be there, and that's 30 degrees between pairs. Welcome.
Now that the Rick say that we should be calling phases lines. Because that makes sense because it's the phase and it's the line.
Yeah, but
they're saying each phase is you should call them line 1, line 2, line 3.
Yeah, but they are, you call them line,
But they're
for
phases.
But the phase voltage is between line and neutral. So you call them lines because the line voltage you talk about between lines.
Yeah.
400 volts. So
phase.
going back, let me put a new one slide in. Here's our star connected. I'm kind of doing this because I know I've got some non-electrical people in the room as well. There's our three-phase generator. We have red phase, blue phase, neutral used to be black in the is. Can I get a yellow pen on this board? I think I can do it like that. Phase. Yeah. What you get out of this system is between each phase and neutral 230 volts. On our system. Yeah. So that's what I know as phase voltage. Yeah. Line voltage between each line. Get 400 volts between that pair. Volts between that pair, and blue and yellow, blue and red, 400 volts between that pair. But what you have to remember is each of those 400s 120 degrees out of phase with each other, and each of those 230s are 120 degrees out of phase with each other, and these is 130 degrees out of phase with its respective line voltage. Yeah. And then they go and complicate as you think. Go and put this and back to it. Why do they do that? Make it safe. You think has to make it safe. All the other earths you put on make it safe because they do that. But if you don't do that, we're connecting to the biggest bit available to us, Earth. Yeah, and we're using that as a reference. We're saying Earth is 0 volts. It ain't going to change. Its voltage level has not changed. So we try that. Unbalanced loop. As the loop changed. Why that's star point down and it doesn't. Yeah. Take that centre point away and put an unbalanced load on there, and you get all sorts of funny things happen. Calculations scoop of what we're going to do. I know it was to not to. So that neutral kind of takes all the input therefore. Yeah. Yeah. Well, because that's there, well, you can get a shock when you put your finger on that phase there. You have to do something about that. Yeah. I don't know exactly how other countries' systems work, but some other countries have earthless systems. They don't do that. I don't know what they do instead. Alright? I always ask my younger students, what's the most important connection in a plug? They go a lot further than the neutral. No, important connections to the Earth. Like neutral work, Earth makes it safe. You've got to get that across to youngsters with electricity, don't you? I think